So we're going to look at motion maps again, and we need to remember that we are using vectors here. Vectors have a direction and they have a size. So in physics, to the right is going to be positive, the left is going to be negative, and then for our size of the vector, the longer the vector gets, the faster the object is moving. So we are going to be using these vectors and the dots to draw our motion maps. So the first one that we're going to look at is example number 2 on this motion map. We are given a position time graph, and you should be able to transition that into a motion map and then be able to give a verbal description. So we're going to start with this. We start with the starting position. You are at 0 meters at 0 seconds. At 1 second, you are at 2 meters. At 2 seconds, you are at 4 meters. At 3 seconds, right here, you're still at 4 meters. At 4 seconds, you can just read these right off the map. You are at 3, or off the graph, you are at 3 seconds, or 3 meters. At 5 seconds, you are at 2 meters. At 6 seconds, you are at 1 meter. At 7, you are at 0 meters. So we can draw our velocity vectors on here between the dots. The more distance between them, the longer the vector. And those are pretty constant for length. And then we were at rest between the second and the third second. So no vector on between those. And then we have a vector between the rest of those positions. We're keeping them constantly the same length. And even at 7 seconds, we're going to put a vector on there because this does not say, it looks like the slope is staying the same. So now we should be able to do a verbal description. We can start out saying the object starts at the origin. We always talk about the starting position. That's the first thing that we get. It moves with a constant velocity of 2 meters per second for 2 seconds. Then it is at rest for 1 second. Then moves in the negative direction at a constant velocity of a negative 1 meter per second. Oops, 1. Meter per second for 4 seconds. The next example, number 3, motion map. We have a motion map. Now we're going to do a position time graph, and then we'll do a verbal description. So this is our start right here, and this is the end. So to just kind of look at that, you need to kind of figure out what that is. So it looks like we need to put some times on here. Okay, our start is we're starting at 5 meters. So then the next at 1 second, it looks like you're at 4 meters. 2 seconds at 3 meters. 3 seconds you're at 2 meters. The 4th second you're still at 2 meters, right? Because here's this the 2 meters. So there's 0, 1, 2, 3, there's the 4th, there's the 5th second. And the 5th second, we're still there. The 6th second, we're at 1 meter. Right here, 6 seconds. The 7th second, we're at the origin, 0, and we're also there at 8 seconds. and at 9 seconds. And then we start to move again, and at 10 seconds, we're at the 2 meter mark, and at 11 seconds, we're at the 4 meter mark. So the graph looks like this. So we should be able to transpose between the two different things. So then if we wanted to do a description on here, we would say the object starts at the 5 meter mark. It moves with a constant velocity. I'm going to abbreviate that. And this is a negative velocity. It is a negative 1 meter per second for 3 seconds. And then it is at rest for 2 seconds, then continues with a constant velocity, and it is still negative, and it's still a negative 1 meter per second for 2 seconds. Then it is rest again for 2 seconds. And the final movement, it moves with a constant velocity that is a positive 2 meters per second for 2 seconds. So that would be our description for that one. So we need to remember the difference between distance and displacement. So this is kind of a diagram that shows us. So the displacement is, what is your change in position from start to finish? So that would be that direct measurement from start to finish, the green arrow. And then the distance is the actual path length that something travels along. This is what they did. Okay? So if you drove in a circle, what would be your displacement? It would be 0, but your distance would be whatever the circumference of the circle is. So we're going to look at one more example here, and then we're going to go to a velocity versus time graph. How would we draw this, and what does some significant information on that graph represent? So if we were to look at this and do a verbal description, would we say our object is going to start at the 2 meter mark? Each one of these is a meter, so this is 0 meters. So the object starts at the 2 meter mark, moves with a constant velocity of 2 meters per second, and there's a positive, that's positive, so we know it's in the positive direction for 2 seconds. Then it is at rest for 3 seconds. So here's the rest. There's 1 second, there's 2 seconds, there's the 3rd second. Then changes direction and moves with a constant velocity of a negative 2 meters per second. The negative means that a change direction for 1 second, and then at rest. There is no vector on that, so it is just standing in that position for 1 second that we see. Now, I'm going to want to take this motion map and I want to graph it on the next page. So I'm going to take the information from the motion map on the previous slide and put it on this slide. My starting position at 0 time was 2 meters. And then at 1 second, I was at 4 meters. At 2 seconds, I was at the 6 meter mark. And then I was at the 6 meter mark for the next second, and the next second, the next one. And then in the final one, I ended up back at the 4 meter mark. So it looks like my position time graph looks something like this. Okay. Now, when we have the position time graph, the slope on this position time graph is significant. Remember we said this is the velocity. If I did the slope for this, it would be position final minus position initial over time final minus time initial. And so I'm just going to look at this part right here to begin with. I know the slope of this area right here, that is 0. So if I look at these, my position final was 6 meters minus my initial position was 2 meters over my time, which would have been 2 seconds minus 0. It looks like I get 4 divided by 2 equals 2 meters per second. So that's what my velocity is, because we know the slope equals that. So I would go over to the velocity graph. I went 2 meters per second. It's constant, so we're going to keep that a horizontal line, constantly the same value, for 2 seconds. Okay. Now, this is 0, so that means I wasn't moving. So we know you would have to slow down, but we're not interested in that time of frame when you slow down. So to do that, we're going to say, yeah, we know something happens here, but we usually draw it as a dashed line. And we're going to say you were slow, you were at rest for a period of time, and it looks like it was for 3 seconds. So we're going to do this for 3 seconds. At rest, right on the 0 velocity mark on the graph. And then the last one is, if I calculated the slope of this line, I have 4 minus 6 over 6 minus 5 for seconds. This was meters. So it's a negative 2 over 1. It looks like I have a negative 2 meters per second. So to do a negative 2 meters per second, I know that my speed has to change. I'm going to do that dotted line, and then I would draw this right here. That would be my negative 2 meters per second. So that's how I would transpose my position time graph into the velocity time graph. I would calculate the slopes for each segment, and I had 3 segments here because I had this type of motion here, and then I had this for my second. So this is my first type of motion, this is my second segment, and then this is my third segment. So I would use those to calculate that. So we're looking at this graph, and we want to point out some significance on the velocity versus time graph. If we shade in this area from the velocity to the origin of the time graph, this area, to calculate it, it is just base times height. The base is time, the height is the velocity. Velocity times time, that should be something significant to us. That is the change in position. That is the displacement. So the area underneath this graph represents the displacement. If we looked at this, the time for this would have been 2 seconds times 2 meters per second. Seconds cancels out. We end up with 4 meters. That is the displacement that this object traveled in that time. If we did this area, it would be a negative 2 meters per second times the time of 1 second. It would be a negative 2 meters. Seconds would cancel out. So the displacement during this time frame was a negative 2 meters. Now, if we want to figure out the net displacement, it would be sum up the displacement. So it's the sum of the displacements. So we would take the 4 meters plus the negative 2 meters. We know the net displacement for this object is 2 meters. So in other words, it is 2 meters right of where it started.